Our next speaker is Josh Kenkel from BTS of CTBTO. His presentation about the status of radionuclide source location exercise for the automatic data fusion tool at CTBTO. You have 15 minutes and keep 3 of them for the discussion, please.
I'll try, thanks. So thank you. So this is some work that it's been ongoing at the CTBTO with a lot of help with my colleagues. So at the CTBTO, we do our data fusion. This is our automatic tool that produces matches between SHI ellipses and radionuclide samples using the atmospheric transport modeling. So you can see a little diagram here how we may have an SHI ellipse, and when the SRS field associated with the radionuclide measurement overlaps it, we mark that as a match. And we provide this on the secure web portal for users to further analyze. However, we've gotten information back from users that actually there's too many matches, it's difficult to prioritize, and it's difficult to come to a conclusion because there's too much information. So we need to help users to condense that information. So as I said, we use the atmospheric transport modeling. So just a quick run through of what that's telling us. So we do backward modeling from the station, and that lets us make inferences between the station and the source. And there's two questions we can answer. One is, would the plume arrive? And the second is, what fraction of released particles would arrive to the station? And that's the dilution factor. So then we have this equation. If you know the release R, the dilution factor D, and you incorporate the radioactive decay, then we can estimate the measured activity concentration. At the CTBTO, we run backward simulation for each sample, and we get this produces our SRS results. These are gridded into a spatial grid of 0.5 by 0.5 degrees in latitude and longitude, and in 1 hour time steps up to 14 days in the past. And we use both ECMWF and INSEP wind fields. So this setup, this gridding, is going to then imply how we do our model later. So as I mentioned, we want to help users to get the information really more precise. So the idea here is that we can use an automatic radionuclide source location, so essentially treating the radionuclide network as a network, like we do on the SHI side, to bring the information together. And there's a lot of research that has been done on this. I give one example here from the FREER software, but there are many ways to do this. You can use PSR, cost function, Bayesian inference, which is this one. And this is available as an expert tool, but it doesn't immediately lend itself to an automatic processing. So in this work, we look at a global reconstruction method, which is aimed towards that. So just to make that more precise, on the left-hand side, if you want to do a local reconstruction, it requires somebody to actually go and choose which results are interesting and put that into the software to then get out a result. So this is manual, and it's difficult to automate. The idea behind global reconstruction is you just take everything and put it into the model and then get out some information, therefore avoiding the human step. So how do we do that? The way we've chosen is to use a log likelihood ratio. So the idea is to give a score which represents the probability. And the log likelihood ratio is useful because the formulation is there in the middle. What it does is it compares a null hypothesis to an alternative hypothesis. And you maximize the likelihood under the null hypothesis, compare that to the maximum likelihood under the alternate hypothesis. And you can see the log turns products into sums, which is very useful because it's more numerically stable, and it makes it more easily interpretable. So you can see when we break out to the sum, we're really comparing the two, the null hypothesis and the alternate hypothesis. If they're similar, that means that they have the similar explanation. But if it's large, that means that the alternate hypothesis is more fitting better. So that's what we're looking for. So we need to define these likelihoods. And so for this probability model, we do something very simple. We just say, okay, as a function of time and location, we just look at the joint probability of a release. So if there's a release, then it should result in detections, and you'll also have non-detections. So we just say all the observations should be consistent based on that. So if it's detected, we have a probability detection, and non-detection, 1 minus that. Then we need to actually figure out the probability of detections, and we can use the ATM for this. Now, there are different ways to consider the ATM for this, and one is of ensembles, and that's an ongoing work. In this case, I'm going to use a historical method. In here, just to say, I break it down into 2 pieces, which I'll describe next, whether it arrives and whether it's compatible with the measurement. So what we do is we look over 10 years of ATM simulations and generate hypothetical releases. And we say, okay, if we put a release here, does it arrive to the station? Do that over and over again, and just take the ratio of the number of results we get, positive results over the total. And that's what this map here is. For one particular station at one particular time, it gives the sort of a probability distribution of would that arrive to the station at that time. And that's this term here. And on the other hand, we can look at the dilution factor, and once we know, or we input a release and a decay factor, we can compare that with the measurement. So we have a predicted measurement, and we compare that with the measurement, and based on the radionuclide measurement and the uncertainty on that, we can make an integral. So that gives us a compatibility. And this is then brought together into the model. As I said before, the likelihood, or the log in the likelihood, turns products into sums. And so we can apply this across all stations, and they become a combination in the sum. So how do we apply the model? So I'm focusing here on the radio xenon network. And as I said, we have detections and non-detections. So here we have a categorization scheme. We have level B and level C, which are exceeding the Curie limit, and or the critical limit. Those are detections, and anything that's not level B and C, which are level A samples, are non-detections. So now we can evaluate these using these synthetic sources, evaluate the model in time slices, and when you choose a time slice, then you say, okay, anything that could affect this in the last 14 days, which is the time of our ATM simulation, is input to the model. You do the sum, maximize the likelihood over a set of released activities, and consider the null hypothesis, just that the release activity is below some threshold, and this would be a hyperparameter in the model. So it's tunable, but we have to choose something. So this is just one test scenario, and in this case, you can see that the source location there, and that you get some sort of score distribution, which indicates the compatibility with the measurement. And you can see it's quite a large blob over a large area. But so let's just choose a region of interest. So if we take a threshold on this color scale, you can imagine that we can select this region, and even possibly select multiple regions based on different possible sources. Then once you select a region, you can then inquire what went into that region. So here, I take an average over that region and say, okay, what happened? Each sample contributes to the score, so now I'm breaking out the pieces of that sum, and then we can sort that. So now we have a sorted list of samples and the score, how it contributed to that ROI on average. And this is nice because now we have a list of samples that are relevant to that ROI. So this is sample association if you make this choice of threshold. So what we've laid out here is a way to do sample association based on an automatic process. And since we since we've used this historical data, it gives us an easily interpretable sample association. So now we could keep going and do source reconstruction, et cetera, or we can take this and put it into our other reconstruction algorithms. So we can, for example, take this and put it into Freer. So this is what we did here. So on the left is this result that's sort of just zoomed in to match the maps. And this is inputting the same information to Freer. This is the Bayesian reconstruction. And you can see that it's done a lot better in getting the source location more in a more smaller area. So this is now laid out a procedure for doing this. So this is sort of a first step in getting in how we can improve the automatic data fusion tool through radionuclide source reconstruction. And this global model is really, it gives you an easy way to make an explainable, let's say, first guess, and then we can go further and say, okay, now what is it telling us? We can put it into other tools, and it really potentially removes a blocker to automatizing our source location. So the next step is to generate a large-scale set of synthetic data that'll help us to evaluate this, understand it better, and tune hyperparameters, and really figure out if this can really work as an automatic tool for data fusion. Thank you.
Thank you. And we have time for a couple of questions, if any. Please, Martin.
Yeah, well, thank you very much, Josh. Very interesting work. It reminds me a bit of what Harry Miley presented last time, sample association. Is this approach different or similar? Can you explain the difference? And may I ask a second question? I got lost about fusion, the fusion concept. Where do the seismic events come into this?
Right. So let's say it's at least motivated from Harry's work. So this has been evolving over a few years, sort of starting from those same ideas. So we'd have to see how similar it is, but it's incorporating those ideas and bringing it to something here. Now, when it comes to the SHI side, I mentioned it at the beginning, and the simple fact is we have the network location. We have event locations for SHI, and they're very, compared to the radionuclide side, they're very precise. So here, mainly focusing on getting that information from the radionuclide side to bring it together. Then the next steps of how we take further information from SHI and RN together, I think we can talk about that and make improvements. But so this is sort of the step before that, let's say. Thanks.
Any other questions? Yeah.
Josh, really very interesting. My question would be, could you a bit elaborate on the difference? So you're also working with likelihoods, the differences between Freyer and your approach?
Well, yeah. So the Freer is a Bayesian inference using a Markov chain Monte Carlo, and so when you do that, you give it the actual SRS fields that are relevant to the specific measurements. So it's using that information, and so it's a little bit sensitive. Let's say, if you give it something that shouldn't be associated, or if you add noise, then it sort of makes the results not as either you don't get any results, or you get a inconsistent result. Whereas for this method, it's bringing in this historical ATM information, which is certainly too much. It gives you too broad distributions, but in this way, it can give you a guess. It can give you an automatic way to get a guess at where something is happening, and then to feed it into that tool. So it's a bit simpler, a bit different, and yeah. So I think these two different methods can work together. Like I showed here.
Thank
the climatological
Yeah.
approach, or because you use historic
Right.
weather data over which period? I did not get
Yeah,
this.
it's 10 years. It was
10 years.
approximately 2014 to 2024. Yeah. But the idea is to grab enough statistics over time so that you have your probability distribution is describing the full range of possibilities that you may encounter.
Any other comments or questions?
Hopefully a quick one. Regarding your next step about synthetic data, do you have any ideas or plans on how to generate it?
Yeah, I actually didn't mention here. So at the PTS we have simulations with ECMWF and INSEP. So these we can compare ECMWF to INSEP. But I think if we really want a good representative set of synthetic data, we need to consider backgrounds. We need to consider multiple sources. So it's something I've been engaging the community on, and how we can pull in all this information and really make a robust set of synthetic data. But that's a work in progress, let's say. But it's something we need to address so that we can really have a solid comparison, a solid evaluation of these tools.
Any final comments or questions? So thank you, Josh, for presentation, for replying comments.